Welcome to Webinar Wednesday. On behalf of the Powder Coating Institute, thank you for joining us in today's webinar. How many automatic guns are needed to coat a part? Presented by Jeff Hale with GEMA USA Incorporated. Before we start, I would like to remind everyone that all attendees are on mute, so if you have any questions along the way, please type them into the questions panel. The speaker will address the questions at the end of the webinar. If we run out of time, contact information will be on the closing slide if you have additional questions. This webinar will be recorded and available through the PCI store within 2 business days. All attendees will receive a brief survey after this webinar. Please take a few moments to reply. We appreciate your feedback as PCI continues to develop new programs to offer the topics and trainings you need. Now I'd like to introduce the presenter for today's webinar. Jeff Hale is the Director of Marketing for GEMA with 35 years of service. He has held a variety of positions within GEMA, including engineering, product management, territory sales, sales and distribution management, and marketing. Throughout his career, Jeff has given many presentations as well as written several articles on the powder coating process for various societies and trade publications. Jeff is a 1987 graduate of Purdue University with a bachelor's in science degree in mechanical engineering technology. Jeff is a recipient of the United States patent and an active member of the Powder Coating Institute. Jeff, take it away.
Thank you, Kevin. Appreciate it. I'd like to begin today's presentation by just talking a little bit about how to powder coat, and that's really what hopefully all of you are here to learn a little bit more about. What does it take to actually coat a part automatically? I'm going to go ahead and stop sharing my camera here so we can kind of focus on the presentation itself. Let's begin. Oops, there we go. So how many automatic guns are needed to coat a part? It's a question a lot of times people are asked within the industry. Do I really have enough equipment to be able to coat a particular item that is being put on my production line? So there's a number of things that we need to understand. And today's webinar hopefully will help you to be able to understand how you can begin to calculate that. It's not something that is done by just a real hip pocket guess or swag, as some people might say. There really is a mathematical way to calculate that. We're going to review that in this presentation. We're also going to talk about analyzing the application. As we figure out how much equipment is needed, there's some decisions that need to be made about how we might want to effectively coat the product. And so kind of understanding some strategy is another part of this application analysis. We're going to use standard industry information that is available within our industry that all of us in the equipment business or in the powder coating business use from a standardization standpoint. We're going to outline the various calculations, and I'll point to some areas of where those calculations can be found in other publications for references. We're going to discuss, again, as I mentioned, some of the decisions required to determine the best arrangement for proper coverage. But all of that is really leading us to how do we calculate the number of automatic guns. And in this day and age where we have a lot of conversation about artificial intelligence, and supposedly artificial intelligence can can determine so many things and make life easier. So one of the things that I thought would be kind of interesting is, does today's AI really know even how to calculate how many automatic guns are required to coat a part? What was interesting is I put something into ChatGPT, the very question, how many automatic guns does it take to powder coat a part? And I was kind of intrigued by the response. Now, ChatGPT is more of a social artificial intelligence, so it doesn't really get into a lot of, at least from what I've been able to determine, a lot of the theoretical, real deep calculations. That's another level of AI that I think most people are have to pay to subscribe to. But in this free version of artificial intelligence, I was pleased that it came up with the basic parameters that are required to calculate how many automatic guns are needed to be able to code a part. And I'll just review some of those that you see highlighted on the screen to the right. Determine the coverage area per gun. So that seems pretty obvious. How much product are we having to cover? What are we trying to cover? What's that total surface area? So how do we calculate that? And it gives you some references in the general description there. We also have to know how thick do we want the coating. AI is at least smart enough to know that for us to be able to determine how much powder we need to put on, we want to know how thick does it really need to be. What's our performance requirements is really what AI is asking us. What do you need to be able to get a good quality product? And so it knows that we're going to need to calculate based on some of these previous bullet points that we're going to come up with some volume of powder that has to be sprayed, or calculate the total volume to be used. It also knows that powder coating is not 100% efficient. So there is some inefficiency in the process, and obviously thus some overspray, and that has to be factored into the calculation as well. Ultimately, we're going to come up with a total volume per gun, and we're going to determine, at least either determine, or we're going to have provided to us some capacity that our powder coating gun can actually produce. And out of that total volume divided by the gun capacity, we should be able to determine the number of guns. And wouldn't you know it, even as generic as that description is on the screen, that is in fact how we are going to process how many automatic guns does it take to coat a part. So kind of taking what is a general sense from artificial intelligence, let's go to a more industry known resource, and that's the Powder Coating Institute. I will tell you that the presentation that you have today, the bulk of it is all laid out in the Powder Coating Handbook in the 5th edition, more specifically in chapter 10. So if you're familiar with this book, or you're looking for a resource that you can refer to, I would highly recommend obtaining a copy through PCI, the Powder Coating Handbook, 5th edition. Turn to chapter 10 and you'll see these formulas that we're talking about and the process of calculating the number of guns laid out in chapter 10 in one of the sections. But in general, we're going to evaluate a theoretical coverage that the amount of, we're going to determine what is this theoretical coverage that powder will cover. And it's going to take into account the coating thickness and even specific gravity. We'll talk about that in a little bit. We are going to then determine what's the application coverage. So we're going to factor in this efficiency and overspray that was mentioned in the artificial intelligence example previously. We're going to have to determine some sort of production rate. How much metal are we actually coating, and how fast do we need to coat this product? All of that is important for us to be able to determine the correct number of automatic application equipment to be able to properly powder coat a product. We will need to know what is the capacity of a typical powder gun. And even in the 5th edition of the book, the Powder Coating Handbook, we give a range that the industry uses. And so that's a helpful guideline to follow as well. Ultimately, we're going to take our production rate and we're going to divide it by some of these other items that we've calculated, application coverage and gun output, and all of that will be factored into the production rate to determine really what is the number of guns that are required to powder coat a particular product. So PCI lays out all of these formulas in their book, and so we thought we would take this webinar and put it into a more condensed presentation that would allow you to be able to kind of calculate this if that was something you were desiring to do. So let's dig a little bit deeper. Let's talk about some of these different areas. The first thing, as we mentioned, you need to know is you need to know total production required. We're going to need to know the coating requirements. So how thick does it need to be? There's a number of different aspects about the coating requirements. We'll review those shortly. We're going to need to know what is coverage. Where are we looking for coverage? And then what is the configuration of part? We really need to understand what types of products are we coating. So let's look at these a little bit deeper one at a time. So from a total production standpoint, you may have something like you see on the screen to your right, where you actually have a variety of parts configured on some sort of massive fixture or racking fixture. And so that represents although it's individual pieces that are parts, and yes, we are trying to coat those, that represents one big massive fixture that you're trying to coat. That's certainly one way for us to look at how many automatic guns. You may have a particular need where you want to evaluate this for one specific component that maybe is hanging on the line. And so rather than a whole fixture of these, maybe you're hanging just one individual piece. Whatever the arrangement of the product is, we do need to understand what are the number of parts that are required for us to process through this powder coating process line or the powder coating booth where we have the automatic guns. So we need to understand what it is that we're coating, what's the number of them, what's the quantity required, really to get a very good assessment of this. What's the hanger and line spacing? And so if we understand each of these, we can begin to maybe build a good hanging fixture or look at evaluating line density to improve that. Because quite frankly, line density, hanger spacing, that will help us to improve our overall transfer efficiency. We'll discuss transfer efficiency a little later, but obviously the more dense the line with product, then the more metal that we coat, the more efficient that we can be in reducing some of that overspray and recycling some of that material or spraying to waste in some examples. But we want to be as efficient as possible. So maximizing our hanging, spacing, and line density is critical to using or get the most out of whatever the number of guns are. But ultimately, we're going to determine some maximum part size. That might be the maximum height. So if I were to use, let me use some of my drawing tools here. Give me just a second. We'll stay with the arrow. So I might look at my maximum part size is from here to here. So we're looking at this distance as my maximum part width, and likewise, or sorry, part height, and likewise from here over to the right side, that would be along the conveyor. And then obviously if we had any depth, so depth across the conveyor would be another way. But ultimately we're trying to determine what is that, let me get rid of this arrow. We're trying to determine what is the, let me go back to my selector tool here. There we go. What is the maximum product size that's going through? What is our production time that's available? And from that production time, we can ultimately determine some sort of production in terms of square footage per hour, per minute, per year. But we can determine what is the amount of material that we need to process in a given period of time. That takes care of the production requirements. From a coating requirement standpoint, we need to have a good understanding of how thick do we need it. Are there primary surfaces that we're concerned about where maybe the thickness is most critical? And there are where we want to ensure that we achieve maybe 3 mils or we have a 4 mil target. And maybe there are some secondary surfaces, maybe it's on the backside or a hidden area where we're not as concerned with the thickness, but we are looking at the amount of powder, some amount of powder that needs to be applied on these secondary surfaces. So understanding where the thicknesses are and coming up with some sort of an overall average for the part is helpful. So coating thickness is important. Do we need to coat this automatically or manually, or will we be doing both? Now, obviously, for the sake of our webinar, we're going to consider coating this automatically. However, depending upon the complexity or the geometry, there may be some surfaces that still require some touch-up to be able to get the required thickness or the coverage that we're looking for. Either doing that with manual or even a secondary consideration of putting in some dedicated fixed applicators to be able to target certain regions. But in general, what we're looking at in this particular case is what is the basic number of automatic guns that are required to be able to coat the product that is passing down the conveyorized production line. We also may have a need to understand the total number of colors and or frequency of changeover. That doesn't necessarily have as much to do with the number of guns, but it is important information from a coding requirement just to have as an awareness, and if we're gathering data, to make sure that we understand those two items as well. From a coverage standpoint, again, as I mentioned, how much has to be covered? Is it based on the part style? Is there a particular rack or hanger arrangement that we're concerned with? How we're hanging these? Where are the critical areas of concern? Are there areas that are requiring less or more coverage? What's the coating thickness? Those are all things in terms of just understanding the coating, the coverage requirements, being aware of that. Secondly is the configuration. As I mentioned, are we doing one-sided or two-sided coating? Is there areas that we need to focus on for performance characteristics, corrosion protection, or is it just simple making sure that some areas are covered, but they're not as critical from a decorative standpoint? Will it be single hung or multiple parts hung back to back? We can improve efficiency by hanging up multiple parts, but obviously depending upon the arrangement, that can begin to mask certain areas. So we do need to be aware of our hanging arrangement, our part configuration. That's important in terms of an analysis. And if there is potentially a need for either a manual touch-up or some dedicated automatic guns for reducing any kind of manual labor that might be required. But obviously a lot of companies will typically put automatic guns in it and then use some sort of manual touch-up, either pre or post, as a way to fill in those areas that may need some additional attention. So with all that being considered, if we have some good understanding of those four critical areas, we can begin to get a better understanding of how many guns are needed to be able to coat a product. And I kind of was having fun. It's kind of like answering the question, how much wood could a woodchuck chuck if a woodchuck could chuck wood? It's kind of like how many powder guns does it take to be able to coat this product? So in general, we're going to try and answer that question. And so let's just dive right in and begin. One of the first things that we need to understand is what is theoretical coverage. So we need to understand how far will a pound of powder go. So it's kind of like what's our average gasoline mileage per hour for our car that we drive? What's the theoretical mileage of that engine, right? And so in this particular case, we have a formula that you see up in the corner. And theoretical coverage is the amount of square footage per pound of powder. How much metal can a pound of powder cover? And one of the key things that we want to do is we want to factor in specific gravity. But let me say, before I get into that, the question is, where is 192.3 come from? That is an industry universal powder constant. That is what the industry recognizes, that a pound of powder will cover 192.3 square feet, but that is based upon a specific gravity of 1, a coating thickness of 1, and an efficiency of 100%. Now, those of you that come from the liquid side of the business may recognize that a gallon of paint will cover so many square feet of metal. It's a similar kind of constant we have in the powder coating world. And that's why I've highlighted it in red. That's our industry standard that is used throughout the industry. And this, so generally, all of the powders that you buy don't have a specific gravity of 1. They're generally heavier than that or have a higher number. And the cured thickness is usually greater than 1. Generally, it's probably 2, 3, maybe 4 mils in some applications that are more. And obviously, as I mentioned, we're not 100% efficient. So we have to factor in efficiency at some point. But our theoretical coverage is going to take into account the industry constant, and we're going to factor it down for the specific gravity. Now, where do I get that? The specific gravity is provided by the manufacturer, powder coating manufacturer, and it's usually found on their technical data sheet, the TDS. You will find that typical range of powders for the specific gravity is from 1.1 to 1.8. Yes, you could find some that are closer, even below 1.1. There are certainly some that are well above 1.8, but what we see for thermoset powders in our industry, that's a pretty good range. And I would say the average is probably somewhere in between 1.4 and 1.5. And if you're looking for more information as to what is involved with specific gravity, I would refer you back to the powder coating handbook for some more information, or certainly consult your powder coating manufacturer to help them understand a little bit more about specific gravity. But we do factor that into this, as well as I mentioned, the coating thickness. So we'll come down to an example a little later where we'll see some of these, but that in essence is helping us to understand what is the theoretical coverage of this particular powder that you are evaluating in this particular scenario. And so then we factor in the efficiency. So application coverage is the theoretical coverage, TC, and factoring in the transfer efficiency. So application coverage, again, is square feet per pound, but really it's the factoring of the efficiency of the process. Now, if you want to learn a little bit more about transfer efficiency, again, I would refer you back to the powder coating handbook. And there is also although it's for a lab environment, it does help in the back of the powder coating handbook. I think it's Tech Brief number 10. It's on page 330. There is an example of how you can calculate transfer efficiency. Now that's based upon a laboratory environment, but it does help you to better understand what's involved. And transfer efficiency is really nothing more than the amount of material that is applied to the product in a given period of time, and versus the amount of powder that was sprayed in that same period of time. And so the more we apply to the product, the more efficient the product is. Theoretical coverage is, again, is the previous formula that we calculated, and so that helps us to understand how these two dovetail together. So let's keep going. So we mentioned we now have a better understanding of how much a pound of powder will cover, and so we also then need to look at our production rate. Our production rate is basically the amount of square footage of material that we plan to process on this conveyor line. So our production rate is generally thought about in terms of square feet per hour, square feet per minute. In this particular example, it would be square feet per hour. So the product height to be coated is, again, the maximum is the product that's going through our conveyorized line, and we are looking at how many feet high is this. And so our production rate is taking into account the line speed of the conveyor. And in this case, we will take the product height times the line speed. So we've really simplified our square foot calculation, because really automatic guns that are spraying in a booth are looking at a wall of product that is coming by at a particular speed. That's our conveyor speed. So it's a simple way to do the calculation, which is looking at product height times the line speed, and the 60 is our units conversion to get us in to kind of make the hours and minutes work out here. But our production rate then would be a number that we will use. So the question is, how many guns are needed? So in this case, to the number of guns that we would use in our particular scenario here, or in our calculations, would be NG, the number of guns required. And to do that, we're going to take the formula that you see on the right side of your screen. We're going to look at the production rate in square feet per hour. We're going to look at the application coverage, which is our overall applied, the efficiency of our application in square feet per pound. We're going to factor in the number of sides coated. So the sides coated is whether or not we want to evaluate our application from only one side of the part, or do we want to look at it as a total, looking at both sides of the product. So it does make a difference which number you use, but you're only going to use 1 or 2, the number 1 or the number 2, one side or two sides coating in the SC category here. And then we're also going to put in the amount of powder that we think is coming out of our guns. Now, this can actually be measured. And if you're looking for information about how to do that, I would talk with your equipment supplier. That's a very simple and easy way to calculate the amount of material that is coming out of your spray gun per minute or per hour, however you choose to evaluate that. In the powder coating handbook, we give you a working range that typically is between 18 to 29 pounds per hour. For those of you that are working in metric, that would be a range of roughly 145 grams per minute to 220 grams a minute. So depending upon what type of units you like to work with, the typical ranges that you see most of the manufacturers trying to drive their or use their equipment in. And I'll say this as an example. This does not mean that the maximum amount of powder that can come out of a powder gun is 29 pounds per hour or 220 grams per minute. That's saying this is our ideal range to work in. Typically, like you would drive your car, you never want to drive your car with the accelerator all the way to the floor, because you would wear out your engine, you use more gas, you use more oil. And likewise, we would never want to drive a car barely touching the accelerator, because we'd get honked at all the time. We would never get anywhere. So we have to have an ideal range to work in. And that's really what this is trying to give you an example. This is a pretty good range that most of the manufacturers are designing their system. As we typically say, more is not better in powder coating. We can be more efficient with less powder coming out of the guns, but we have to finding that sweet spot, operating spot is really critical. So now that we have a basic understanding of the formulas, let's walk through some of these formulas in an example. So we have a product that has a particular conveyorized direction. We have a length, a width, and a height. In this case, we're going to run our line speed at 15 feet a minute. We're going to evaluate the application. We're going to evaluate the total number of guns that are required. So we're going to use a sides coated of 2. That means both sides will be calculated in this example. We're going to come up with a specific gravity of 1.4, rather what I would call nominal or average range specific gravity of powder that you would find in the industry. We're going to use a coating thickness. In this particular example, it's going to be pretty low, 1.25. And that's well, anyways. So a 1.25 mil is a very low film thickness. But for this particular part, we're going to have a product height of 5 feet, a length along the conveyor of 3 feet or 36 inches, and a width across the conveyor of 1 foot. And I see it says width here on my screen, but on the little example that would be depth, sometimes width and depth can sometimes be interchanged depending upon your perspective. But in this case, the example 1 foot would be the width across the conveyor or the depth across the conveyor, either way. Our transfer efficiency, we will assume that it is very moderately efficient, so it's a 60% TE. And our gun output, we will put at a range of about 26 pounds per hour. So we're still within that window that we would like to operate. So in this particular case, we're going to use a fan spray, which is, I'll get into that, why we are choosing that here in a little bit. But in this particular example, we will use a slotted fan spray nozzle, which can be configured either vertically or horizontally. And so you can see that if I turn the pattern vertically, it's 2.5 inches wide and 10 inches tall or height. Likewise, if I turn it horizontally, the numbers flip. It's 10 inches wide and 2.5 inches high. So it's important for us to understand the pattern, approximate size of the pattern. And we'll walk through these examples here as we go through. So our theoretical coverage is, again, using our formula that we reviewed earlier. So we will put in the numbers of 1.4 and 1.25, and we can see that our theoretical coverage is 110 square feet per pound. Likewise, we want to factor for efficiency. So our theoretical coverage is 110, as we just calculated, but we're going to use the transfer efficiency as our way to, again, show that we are not as efficient as we would like to be. And so that theoretical coverage is factored down. So we can't cover as much because we're not 100% efficient, we're only 60% efficient. So in this case, our actual application coverage, a pound of powder will only cover 66 square feet. Our production rate is taking our line speed and our part height of maximum part height of 5 feet, and we're putting that into our calculation, and we can determine that there's 4,500 square feet in an hour that our production rate is producing. So to determine the number of guns, we're going to take our production rate of 4,500. We already determined that we were using 2 sides coated, and we are just calculated our application coverage. So that's 66 square feet per pound, and our gun output we established in the previous slide of 26 pounds per hour. All of that tells us, we work through the math, that this particular example, 6 guns are needed. Now, in this particular case, we utilized the sides coated of 2. So the 6 represents a total number of guns needed to coat the product. And in this case, 6 guns or 3 per side would be used in our conveyorized application. So the question is, we need to do a little bit of an analysis. And number 1, is this enough guns? Could I be utilizing fixed guns, or is there an alternate way? If I'm going to be using fixed guns, what's the spacing of the guns? And if I'm going to be using perhaps maybe even a gun mover, what does that look like? What is the stroke and speed that's required? What type of gun tip is used is another piece of this that we need to at least factor into our analysis. So now we know that 6 guns is required to spray enough powder to cover at our particular coverage rate, but we need to do a little bit of an application analysis to make sure that that is enough guns. So let's walk through a couple things. Number 1, it helps us to understand what's our spray size. So really, to do a proper evaluation, we need to understand what type of tip are we using and what is its effective height and width that is generated from the gun. And I'll liken this to, if I gave you a wall to paint in your house, and I said, okay, here's a gallon of paint, cover the wall of this, and you have a limited time to do it, you would likely want to use the widest brush possible. It would be a lot faster with a 6-inch paintbrush as opposed to a 3-inch paintbrush or even a 1-inch paintbrush. As you can imagine, each of those brushes generates a certain width or effective pattern that is as we stroke the brush along the wall. And a powder gun is really no different. It's based on the type of tip that's used, and so understanding whether to use a flat spray or a deflector, either one, there's certainly a whole nother conversation to have as to the advantage of each of those, but you do need to have a relative sense of how wide and how tall the pattern is that is generated from the spray gun regardless of the type of tip that you're using. We also need to understand the maximum part height. Do we need to, will we have to spray above the product, below the product? What if they don't need to even go over the product? So we need to understand think through what is required, how deep or wide is the product, and how do we evaluate this? So this effective pattern height is important. That's our EP with a sub note of H there. That's our effective pattern height. And our maximum part height max, those are going to be used to help us to determine whether or not we have the right application. So let's walk through a little bit of an example that helps us to understand this more. In this case, we're utilizing a flat spray where we are vertically orienting the nozzle. So vertically means the 10-inch high or height of the pattern, as well as the 2-inch width of the pattern. And in this particular case, we would want to perhaps have a extra coating above the product because there's a certain amount of depth. Let's just say in this particular example, we want the full 10-inch pattern to go above the product as well as below the product. So we've determined in our analysis and thinking through how best to coat it, that that's what's required to coat the product. So we need to factor that into our overall part height. So in this case, we're going to what we call overcoat, or I use the word overstroke. That's really more related to a reciprocation, but we're going to overcoat the product in this case, both above and below the product. Oops, let me I didn't want to get ahead of myself here. So the maximum height in this case is our 5-foot product plus the 2 10-inch patterns, which makes the overall maximum part height 80 inches. So our part grew in height because we want to have the spray guns to cover this. So in this particular case, our fixed gun application would be as follows. The number of guns is determined by, in this calculation, by taking our maximum part height, dividing it by our effective pattern height, and we're also then evaluating whether we want to look at per side or the total application. So that's the sides coated. So in this case, our fixed gun example would be maximum part height, and we can see that we have the 80 inches that we looked at previously divided by our 10-inch high pattern height. So 10 inches into the 80 times the 2 sides coated means in this application to have a gun every 10 inches so that the patterns are overlap or just uniformly blending together. I would need 16 guns to coat this same product if I wanted to arrange them in this configuration. So you can say, well, wow, that's a different number than what we calculated before. So let's look at that, a quick review. The 6 guns that we calculated just a moment ago was based on coverage capability for how much a pound of powder can cover given the thickness and the specific gravity and the efficiency. So we can spray enough powder out of 6 guns to be able to coat the product, but what we also determined was to be able to arrange those 6 guns if we wanted to coat it where we are stacking the guns vertically and every 10 inches, we needed to add more guns to the application to be able to use fixed guns. So is this acceptable? Maybe, maybe not. If you are in a situation where you already have 6 guns, you would need to buy more guns or come up with an alternative method. An alternative method could be utilizing gun movers. So let's take a look. Would utilizing 6 guns with gun movers be an alternative solution for this particular application? Let's make sure we understand what are some of the considerations for a gun mover. Typically, a gun mover will use less guns than a fixed arrangement. That's because we're basically moving the gun across the surface, so we are able to cover more area as the product is passing by. The gun, obviously, as you see from the animation, is stroking up and down. So everything is perpendicular to the conveyor. You'll hear terms of short stroking. That's generally what the industry refers to as 6 to 24-inch short stroke dimension. In other words, the gun is moving 6 inches up or 6 inches down to a maximum of 24. Once you get above 24, the industry kind of looks at that more as a long stroke application, but it doesn't really matter whether it's long or short. You're calculating an arrangement of the guns in some configuration where they're moving on the product. Ideally, we want to have the unit, the gun mover, stay within the speed limits of the machine. Generally, as you'll find as referenced in the powder coating handbook, the maximum is 100 feet a minute. We want to move it as slow as reasonably possible, but most of these machines do have kind of a speed range that they work ideally in, just like our gun output. But as an industry, we've said we really would prefer that you kept that under 100 feet per minute. We do consider understroke and overstroke. In other words, just like we did on the fixed gun, how much above the product do we need the powder gun to spray? How much below the product do we need to spray? Perhaps we don't want it to overspray and above. We want it to stay within the dimensions of the product. That's what we call understroking. Ultimately, we're going to come up with a W pattern, and that's because the gun is moving up and down as the product is moving across along the conveyor line. That creates this W pattern. Much like you can get with a fixed arrangement, if the guns are not arranged so the patterns are overlapping correctly, where you would see striping, heavy bands or light bands, you can still see light bands and heavy bands, but instead of it being a horizontal line across the product, you see it more as the shape of a W. And that's where we talk about optimal gun movement, is where we are basically getting the speed of the conveyor in concert with the machine. And so we have to take into account the effective pattern width to be able to do that. So gun mover speed is known as a cycles per minute, and the effective pattern width is, we've already established that, is in inches. And so our conveyor speed we would know in feet per minute. So we're going to look at a formula that takes into account all of those. So in this case, the cycles per minute, or the speed at which the unit is moving, is the line speed times a units conversion divided by the effective width, pattern width. So our stroke, in this case, is how far does it travel? In other words, stroke is generally 1/2 of a complete cycle. So we go up and we go down, that's a cycle. The stroke is really half of that. The number of guns per side we've established through a couple of these different formulas. That's basically whether we're looking at one side or two side. And so in this case, we're going to evaluate this from a one side application. And we need to understand the effective pattern height. So we'll walk through an example here in a minute, but our stroke is basically calculated by looking at the maximum part height minus the total effective patterns, the number of guns that we have. And so let's just walk through a little bit of an example where we can see how this is utilized. So in this case, I have one more formula to review. Gun distance is the vertical spacing between each of the guns on the gun mover. So we're going to need to know how fast does the machine move, what's the spacing of the guns, and how far is the gun moving. So the gun distance is calculated by looking at the stroke and adding the effective pattern. And I'll walk you through an example here so you can see this with a little bit more clarity. So here is our gun distance. As I mentioned, it's stroke plus the effective pattern height. As I mentioned, we also need to have a speed check. So just like you do in your car, we want to make sure that we speed check our application. So in this case, our total stroke is basically looking at the stroke times 2, and we put it through a formula where we're going to calculate the total stroke. And we're basically checking to make sure that the gun does not exceed 100 feet per minute. And so I would always encourage you to consult with the manufacturer of the gun mover to make sure that you're operating within the parameters of their speed requirements of their machine. But in general, this is how you would calculate gun speed in feet per minute, knowing the variables that we've established already. So let's look at an example here. In this case, we're going to be turning the pattern horizontally to get the most effective use out of it. So our pattern height changed from our previous example. Now we are doing horizontal, so it's 2.5 inches high and 10 inches wide. So in this case, we're going to overstroke the part just like we did in the previous example. Instead of going 10 inches, our pattern is only 2.5 inches high. So the overstroke in this case would make our maximum part height, as you see on the screen, 2.5 inches plus 2.5 inches plus the part height gives us a maximum part height of 65 inches. Now, again, as we go through utilizing our gun mover, 65 inches, we're looking for what is the stroke of the machine. So as our formula is laid out, we take the 2.5 inch height of the product times the number of guns on the side. So that's the amount of pattern that we're going to take away from our maximum part height. Those guns are covering that much of the product. And then we're going to divide the residual of that by 3. That tells us that our gun needs to move 19 inches. So our stroke in this example means that the guns are going to be stroking 19 inches. Our gun distance in this case would be, in other words, that's the distance between the guns. That would be adding in our 2.5-inch dimension. So in this case, our gun distance is 21.5 inches. So we're stroking 19, but the distance between the guns is 21.5 inches. Our cycles per minute is, excuse me, is looking at how many cycles in the course of a minute. In this case, it's our line speed times our unit conversion divided by the effective pattern. So our ideal speed of the machine would be 18 cycles per minute. And that is the 3 numbers that we would need to be able to position, excuse me, our gun mover. As I mentioned, we want to make sure we understand what's the total stroke travel. We're going to do a little bit of a speed check here. Our total stroke is 2 times the stroke. Our gun mover speed is, we already established, was 18 cycles per minute. So in this case, we're putting it through our gun speed feet per minute formula, and we can see that that 57 feet per minute is well within the speed parameters that we are looking for below 100 feet per minute. Ideally, we would take this and we could begin to adjust the gun mover at this point, both in the speed or cycles, depending upon if our machine is based on a speed or in cycles per minute, however your machine is set up, and then you can also adjust the guns in the spacing that's determined. So let's just kind of take a brief look at an analysis of our application. We walked through a lot of formulas in a very short period of time, so let's just go back and do a double check here. Based on the coverage capability, we determined that 6 guns was all that we needed to spray enough powder to be able to cover the production rate that we were going to be passing in front of the guns at 15 feet a minute. 6 guns could spray enough, 3 per side, could spray enough powder to give us the mill thickness that we wanted at the assumed efficiency. Then we went through and we looked at a analysis based on fixed guns. So if we wanted to coat this utilizing fixed guns, we determined that we really needed more applicators to be able to cover the product entirely. So in this case, we determined that 6 guns was needed to go up to 16 guns or 8 per side. And then we also did another analysis of utilizing gun movers where we determined that really with the 6 guns, we were operating within the speed parameters and the stroke parameters of our machine where it looks like utilizing a gun mover would be an effective application. So in this case, is the fixed gun arrangement, is it a good or bad? Well, that may be subjective. If you're buying a brand new system, okay, maybe you can buy enough guns up front. If you've already got an existing system, that's probably not going to be good because you would have to make an investment in either more guns or look at perhaps a gun mover. Ideally, the gun mover is a very effective way to be able to do it. And obviously with 6 guns, the gun mover can be used if we're going to stay with 6 guns. So there are options available to you. It's really a matter of trying to understand what's the ultimate goal that we're trying to achieve here. But clearly we've determined that in this particular case, 6 guns would be enough utilizing gun movers to be able to coat the product. So in kind of bringing this thing home to a close, how many automatic guns are needed to really be able to coat the part? Well, you need to be able to consider a number of different things. Total production, you need to be able to look at the coating requirements. You also need to be able to understand what's required from a coverage standpoint, part configuration, and all of that data. Once you know that data, you can calculate what's required to be able to determine the number of guns, and then you can configure and adjust as needed. And so if I may, I'll turn my camera back on here just to kind of again, as a quick reference, if you're looking for more information on how to calculate, I would like to recommend, as I've done throughout the presentation, the handbook is a good, useful tool, as a reference tool. that walks through these, uses these same formulas and helps you to understand how to calculate the number of guns that might be required for a production line application. If you're looking for something, maybe the book is not the right tool for you, I would recommend potentially attending the Powder Coating 202 workshop, Powder Coating Done Right, the advanced class. As a part of that curriculum, there is a day and a half, in the second day, as a part of the lab activity, where you have an application that you are responsible, your team is responsible for evaluating how to coat. You walk through some of the formulas, the presentation, a simplified quick review of the presentation is done in that workshop. So that's another resource for those that like learning more hands-on. With that, I'll turn it over to Kevin if there's no other questions.
Yep, we do have a few questions, Jeff. One, and as you noted, the information is in the book, but also that this webinar can be rewatched after 2 days. It'll be in our store for PCI, and it's basically free for anyone. So if someone else in your organization didn't have a chance to hear Jeff go through it, they can go online there and just view it on the PCI website. But a couple other questions that came in is, what is the basis to assume the transfer efficiency?
Yeah, it's one that I probably could spend a lot more time on. And I guess the simplest way to answer the question is the flatter, the easier the product, obviously the higher the transfer efficiency. The more complexity, the geometry, the more likely it is to be a reduced TE. And that's a hard one for me to say that, for example, if I were to look at bathroom partitions, which are flat panels, those are an excellent example of something that would typically be a higher TE. But TE is also impacted not only by environmental conditions, but also how far away the gun is. And there are other variables that can be kind of impact or influence the efficiency. But in general, you'll see that an automated line is generally, say, 50% efficiency plus or minus 5%. And the more complex the product is, generally the more the lower side it goes. Obviously, if I hung a shopping cart on a production line versus, say, a bathroom partition, the bathroom wall that's used in the stall, the partitions for the stall, that flat panel is a lot easier, a lot more square footage, it's easier to coat versus, say, the shopping cart, which has got a lot of metal, a lot of wire, but a lot of open area. So the more open area, the more geometry, the lower the TE. But it's a difficult question for me to say that every application is going to be, X%. But I would say most of us in the industry, when we're doing an automated production line, are generally using somewhere between 45 and 65% as a general rule to follow, and then we kind of adjust accordingly based on the parameters that we know our own experience. So hopefully that helps you.
Okay, great. Another question, and it says, our powder coat facility is a little outdated, but looking to update. Our line speed is currently 3 feet per minute. The line speed in the example was 15. Is the 15 more close to an industry average?
Great question. I would say that generally you'll find it obviously the higher the production volume, the faster the line goes. I would say in general for a lot of the powder coating job shops, your mid-sized manufacturing companies, that range from anywhere from 8 to as much as probably 15 to 18 feet a minute. That's that sweet spot that we find most companies working in. There are obviously going to be those that are traveling slower, and that's okay, but it may depend on the configuration of the product, the heaviness, how big is the product, how heavy is it, how easy is it to load on the line, and then it's really just how many parts do you need to get out per day. That's really the ultimate deciding factor, is what's your volume that you need to kick out the door to be able to ship, and that dictates your production rate. So 3 feet is slow. It's not uncommon, but it is in the slower side of things.
Okay. What are the benefits to use one automatic gun per side to fully stroke the part?
Great question. So I would say that now you're getting into some philosophical application techniques that are the nuances between the various powder coating manufacturers. But I'll try and provide a more generic response. Reciprocation, where we would utilize multiple guns, either one gun, long stroking, or even taking those same 3 guns that we had in our example and laying them out horizontally, the booth gets longer. So there are some advantages to long stroking the product. We don't have time in the presentation here to get into that, but I would talk with your various equipment suppliers to understand their opinions on that particular philosophy. But definitely the faster you go and the more guns that the application needs, all of a sudden now we have to start stacking the guns vertically to be able to keep the booth as reasonably short as possible and also to have an effective coverage of the product. It's not uncommon to see a single column of guns, but it is more uncommon to see somebody long stroking the product generally. And I think it goes back to the question that was asked a moment ago, is 3 feet a minute slow? If I can long stroke, if one gun can put out enough powder and I can cover the product, long stroking the product, sure, why not? Why wouldn't you want to do that? It's less equipment, you can be more efficient with it. So it's really just trying to evaluate the application based on the parameters of your specific situation and trying to determine what fits best. But I would say in general, you'll find in most of these applications, it's usually 1, 2, maybe as many as 3 columns of guns, and there's multiple guns stacked in those columns because the line speeds are generally higher in those production facilities.
Okay. We got just a little bit more time, a couple more questions here. I've heard mixed things in regards to a perfect single lap, and then having the more laps is better, lower output, gradual film build. What's your recommendation?
Yeah, I would say, again, we're getting into maybe some nuances of expertise or application strategy that each of the individual equipment manufacturers may approach. I can tell you my personal opinion is that if I can overlap the patterns with the reciprocator, and I can do what we would call double coat, even triple coat or quadruple coat, if I can move the machine at a speed where it's within its limits and I can make more passes over the product, I feel like you get a more uniform coating. So now you're getting into some of the strategies of which is the best from a gun mover standpoint. That's a whole nother conversation that we could probably dig into. But yes, more in this particular case, finding that right rhythm of moving the gun in terms of the number of times it passes over the product so that it stays within the speed limits of the machine and you're not overworking it from a stroke standpoint. I think you'll generally find you'll get better uniformity and a better blending of the patterns.
Okay. What is the ideal gun to part distance for automatic fan nozzles?
Oh, wow. It's all predicated there. It's all predicated on what kind of penetration are you needing. Obviously, we want the gun as close as you need it to be able to get the penetration and the coverage that you need. But I want the pattern to be as wide as I can possibly get to be able to maximize my coverage, whether that's arranged vertically, horizontally, or if I'm using a deflector where you get a circular pattern. I have to make sure that I overlap. So I would talk with your manufacturer of your equipment to find out, most of us as equipment suppliers have a pretty good feel for a particular tip as far as at a given target distance, what should we expect from an effective pattern width? And that can help you. But I don't know that there's any ideal range. I just want to be as close as I can to maximize my charging efficiency, but I want to avoid back ionization. The closer I go, the less electrostatics I need, but I have higher particle velocity. So there is some nuances that were associated with target distance. It's really get as close as I need to maximize my pattern, but to reduce the back ionization. And I don't know that there's any hard and fast rule for that.
Okay. Next one, I think is a quick question here. I think just clarification. Are all the examples, assuming stop and go, what happens when you have a continuous motion? And so I think there was a confusion there because this is all continuous lines, is it not?
Yes, yes, it is. These are all, the examples that are in this presentation are predicated on a 5-foot product that was traveling on a line at 15 feet a minute. The guns don't care whether there's a part there or not. I just have to cover that 5-foot dimension or whatever my maximum part size is that I calculated. That's
Okay.
where you start getting into the nuances of what's the geometry, and then you also looking at your density makes for the value. It makes for the justification of looking at some sort of a triggering system that would turn guns on and off in those instances where there is no part, because I don't need powder coming out of the gun.
Okay. We got time for one last question here. Is there a relationship to line speed and number of guns I guess, in a linear? And is there a maximum speed that a conveyor can run before it is not effective at all?
So I don't, if I understood, I don't know that there's a maximum line speed, because as you know, the faster the line goes, the more powder guns we need, because the powder guns can only spray so much powder, and we would assume a particular application efficiency. So the faster the line gets, then it's basically telling you I need more powder coming out of the guns, whether I turn the outputs up or I add more guns. Either way, I've got to do that. So I don't know that there's a maximum speed limit. Certainly, if we want to get up into the 100 feet, 200 feet, 300 feet a minute examples, yes, there's some different nuances there, but everyone in our industry is operating, let's say, 30 feet a minute and below. And those are, we're within the speed limit range. We just adjust accordingly based on the number of guns. And then Kevin, I think there was a question on the linearity of the number of guns. I'm not sure I understood that correctly, but I don't know that there's
it was basically a relationship of line speed to number of guns, I guess in a horizontal direction.
Yeah, no, so line speed can go up, but I mean, there is a relationship, but it's also got to be factored in for the efficiency, the thickness, and the specific gravity.
Okay.
So, yeah.
All righty. Well, that's all the questions, and I think the time that we have today. Jeff, if you could advance to the last slide that has the.
Oops, sorry, wrong way. My bad.
And one more. There we go. So if there's any questions that come up, please feel free to send an email to me. I'll get them off to Jeff, and we can get them answered to you. Otherwise, Jeff, I want to thank you and thank everyone for attending the webinar. Please remember to the PCI website, www.powdercoating.org, for more webinars and training events. We have added a Spanish webinar in August, or actually, that's I think we would have moved that to October now, and the fundamentals of powder coating. So to be sure, check it out. And if you have anybody that's Spanish speaking in your company, have them check it out. Otherwise, please watch for a link at the survey right as you close out today, and take a few moments to give us your feedback. Otherwise, I would like everyone to have a great day. Thank you much.
Thank you very much. Thank you.